Okay, so moving along, there's a couple more terms we've got to define. When we're measuring stuff, we need to be able to communicate how good our measurements are. Sometimes you can measure something and be entirely wrong. Um, and there are a number of places that we can get uncertainty from. The first thing I want to mention is the term uncertainty. Uncertainty basically is your error in a measurement. A measurement where you're kind of eyeballing it has a high uncertainty. A measurement where you're using like professional grade equipment would have a much lower uncertainty than that. Basically, total uncertainty is the amount of error your measurement has. There's plenty of places this could come from. It could come from an experimental issue. It could come from using bad tools. It could come from making wrong assumptions. It could come from um, you and I looking at the same mark and thinking that I think you thinking it looks like 1.3 and me thinking it looks closer to 1.4, right? There's a lot of different places that we can have uncertainty. No instrument ever is going to be able to measure exactly what something's value is. You can't measure down to the atom how heavy something is or down to the atom how long something is. We're always going to have some point where we need to round or estimate. So this is where the uncertainty comes in. Measurements we can describe as being accurate or being precise. If a measurement is accurate, it's close to being correct. So, for instance, a clock that is 15 minutes too fast is not an accurate clock because it's not showing you what the actual time is. Excuse me. Precision um, refers to how much detail a measurement has, usually how many decimal places it'll give you. So, for instance, a phone timer that is synced up with like a cesium clock, which is actually how like Verizon and AT&T submit their times to people on their network. Um, Looking at that, it'll show you fractions of a second. It'll show you down to the like hundredths of a second if you look into exact time. So that is a precise measurement. A precise measurement does not necessarily need to be accurate, though. My clock could give me as many decimal points as I want, but still be 15 minutes too fast. So accuracy and precision are two different things. Accuracy is close to being right, or the known or given value of something. Precision is how detailed it is. Um, and then, like earlier, we said we have different causes of uncertainty. That uncertainty is called systematic if it's from your tools. So if I use my crappy clock or a bad meter stick or something, that's systematic uncertainty. Random uncertainty is everything else. That's like there's an issue in the experiment. There's estimates rounding. There's like some sort of flaw in data. Maybe you're dealing with an irregularly shaped object that you estimated as being a square. Maybe you're dealing with a an object that is not perfectly uniform. Maybe some parts of it are thicker than others. So there's plenty of reasons you could get random uncertainty. So your systematic uncertainty we're going to be able to figure out by determining your tools. Half of the smallest measurement your tools give you will determine your systematic uncertainty. Basically, you're going to round, if you're rounding to the nearest, let's say, millimeter, you have a systematic uncertainty of half a millimeter because you're going to be either rounding it up or down. Likewise, your random uncertainty, basically, because this can come from so many different places, we're going to represent this with standard deviation. Standard deviation shows us how like what the spread of a sample of data is basically relative to the average. So for instance, if I had a data set that was 48, 49, 51, and 52, this data has an average value of 50. If I had a data set of 0, 1, 99, and 100, that data set also has an average of 50. Notice all of these numbers are way closer to 50 than all of these numbers are. So I would have a lower standard deviation here because all my numbers, my maximums and minimums are close to my average. I would have a high standard deviation here because my numbers are far away from my average. In the case of uncertainty, lower standard deviation gives you less uncertainty. So if I'm measuring like this, there's probably a problem. If I'm measuring like this, that's a lot more realistic. Okay. Hi, everybody. It's me, Live Action Asa, back with another quick example. I want to look at, give you an example of accuracy and precision with measurements. So here I've got a tournament legal standard issue Magic the Gathering card, and let's say I want to know what its length is in inches. I know that our base units here in science are going to be in meters, but the best rulers I had to demonstrate this were all in inches, and also the Wizards of the Coast defines the length of their Magic cards in inches, so we're going to use English units this one time. Please forgive me for that. Okay, so here I've got a ruler attached to a hole puncher, and you will notice that this ruler has marks for every half inch. So there's 2, there's 2.5, there's 3, for instance, right? So this is less precise than my meter stick, which has marks every eighth of an inch. So my meter stick is a more detailed tool. It's got more marks on it, so it'll be able to give me a more precise value than my hole puncher will. Let's check this out. So if I line my hole puncher up and I try to measure this magic card, get this as close to this edge as I possibly can, I can now measure this as being like, I don't know, it's right here. I would call it maybe like 3.3 inches, maybe like 3.25. It's about halfway between the 3.5 mark, I guess. So I would say that call it 3.3 inches. That's my final answer. Okay. Now with my meter stick, I'm going to do the same measurement. I can put this end over here, put this end over here. And now notice with smaller marks, it's actually going to be a lot easier for me to measure this card. I'm going to move this closer. So there's 0. Here is 3.5. It's a little bit between 3 and 3/8 of an inch to 3.5 inches. It's almost exactly, actually, now that I'm looking at it from the top, it's almost exactly 3.5 inches. So I would call it 3.5 from here. So my meter stick with smaller increments has a lower amount of uncertainty. There's less guesswork involved in the length of my magic card when I was using the meter stick versus when I was using the hole puncher. And in fact, I googled the standard tournament legal length for a Magic the Gathering card, and their Wizards of the Coast's printers always make them exactly 3.5, 3.5 inches long. So not only was my meter stick's value more precise, it was also more accurate because we know that the printers made this thing to be exactly 3.5 inches, or as close to 3.5 inches as their printers can get them at least. Which is important for a card game because you want to make sure that all your cards are the same size. Otherwise, you can tell when you're going to draw lands or a lightning bolt or something. All right, live action Asa out. Okay, so when we're measuring stuff, we are going to have to round. The way we round is using significant figures. Basically, the difference between a measurement like 100 versus 100.0 is I'm saying that this I rounded to this 0, meaning it's about 100. And this is about 100.0. It is closer to being exactly 100 than this is. This one could have been 100.4. It could have been 99.6. I rounded to this 0 here. If I communicate 100.0, I'm telling you I measured this 0, meaning this could have been 0.4, or this one could have been 100.0 exactly, or it could have been like 100.3 or 100.1 or any of these options. But by writing the 0 in here, I'm communicating to you that I measured it. So significant figures show us what zeros were actually measured and what zeros weren't actually measured. So there are rules we can use to determine the number of significant figures that a unit has, that a measurement has, and we can determine how significant any measurement we make is. When you're doing math also with significant figures, your math is going to be limited by the lowest number of sig figs. What that means is that the least accurate measurement is going to be the one that determines the uncertainty for all the others. So my favorite example of this is like, imagine that you and I are lab partners, and our assignment is to measure out exactly 200 milliliters of water into a beaker. So you measure yours, and you like spend an hour on it. You're there, you're measuring the meniscus, you make it sure it's exactly 100 milliliters. It's 100.0000000 milliliters. It's as close as you can possibly get it. And you put it in that beaker, and it's beautiful, and it's exactly 100. And then I come in, I didn't measure it all, and I just splash about 100 milliliters of water in there. We now have no idea how much water is in that beaker. It doesn't matter how good your measurement was because mine ruined it by being less accurate. So whenever we do math with significant figures, it's going to be limited by the lowest number of significant figures that we have. So how can we tell which figures are significant? It's pretty simple. First of all, anything that's not a 0, you have to have measured it, right? How do I know it's 3 versus 2 versus 1? I measured it. I didn't round. So these are going to be significant. So anything but a 0 is significant. A 0 stuck between two non-zero numbers. So if I have like 0.3071, for instance, this 0 is between this 3 and this 7. I had to have measured it. There's no way I couldn't have, right? By measuring this 7, I had to have measured that 0. So they have to be significant as well. So if it's between two non-zero numbers, that's significant as well. Zeros that come before a non-digit number show scale. So for instance, if I'm estimating this thing's about nanometer, right? That's going to be on the order of negative 10, 10 to the negative 9, excuse me. But all I'm saying is that my units I'm using are really small. Those zeros being in front, I didn't necessarily measure them. They just show scale. So zeros before are not significant. And zeros coming after also aren't significant unless there's a decimal point. Putting the decimal point in there is telling everybody, hey, I measured this zero. The zero is there. I didn't round. Okay? So if there's a decimal point anywhere, the ones at the end do count. All right, let's practice this. I've put the sig fig rules at the bottom of this slide. Go ahead and try to determine how many significant figures each of these numbers has, and we'll come back here in just a moment to recap. Okay, welcome back. Let's go ahead and take a look at what we got. So this first measurement, 18.0083 meters. Well, the 1, the 8, the 8, and the 3 all count because they're not zeros. These two zeros are sandwiched. They're in the middle. So all of these digits count. That's 1, 2, 3, 4, 5, 6 significant figures. Here, okay, my things that aren't zero count, so this 9, this 7, and this 2 do. This 0 is in the middle, so it's going to count. All of these zeros are in front, so they never count. In the beginning, zeros that come before a non-zero number never count for counting sig figs. So here I've got 1, 2, 3, and 4. That's 4 sig figs. Next question. I have 860,430,000 liters. The 8, the 6, the 4, and the 3 all count. This 0 counts because it's in the middle between the 6 and the 4. Zeros at the end only count if there's a decimal point. Notice there's no decimal point here, so none of these count. So I've got 1, 2, 3, 4, 5. That is 5 significant figures. Okay, 1.0400 times 10 to the negative 14th. Okay, so this I added in there as a bit of a test. So times 10 to the negative 14th, scientific notation does nothing but show us scale. So whenever you're looking at a number in scientific notation, you're just going to get rid of it. And if you think about it, that times 10 to the negative 14th is just going to put a bunch of zeros in front of this, which don't count anyway. So whenever you see a number in scientific notation, you're going to ignore it. It's just going to give you scale. It is not going to give you significant figures. So none of those count. My 1 and my 4 count because they're not zeros. This 0 counts because it's in between. These two zeros at the end do count because I've got a decimal point. So this is 1.0400. The times 10 to the negative 5th doesn't count, so that's going to come out to 1, 2, 3, 4, 5 sig figs. 0.000200 pascals. Okay, so the 2 counts, it's not a 0. No sandwich zeros. The zeros in front don't count. The ones at the end do count because there's a decimal. That's got 3. 400.0 Gauss. The 4 counts. All of these zeros are at the end, and they do count because there is a decimal point. So that's going to be 4. That's 4 sig figs. And last, 1.6 times 10 to the negative 19th. Remember, scientific notation does not count. It's got 2. So basically, all of these sig figs communicate to other scientists the accuracy of your measurements. Of all of these, the most, I'm sorry, excuse me, not accuracy, precision. The precision of your measurements, how detailed your measurements are. This measurement here, the top one, has the most number of significant figures, so it is the most detailed measurement. It's the most exact. Wonderful. Let's move on.